All right. So remember what we are doing, of course, solving the Schrödinger's equation in 3 dimensions. We said that the stationary states, the solutions for the Schrödinger's equation, the time-independent part is some function, psi, that depends on n, L, and m. These are quantum numbers. And this is the kind of solution that we are finding for the potential that depends only on R, the central potential. And then we said in spherical coordinates, this solution, this wave function depends on the distance and on the angles. And we separated this. We were able to separate the equations in 2 parts. One equation that depends only on R and the other one that depends on the angle. The part that depends only on R we already solved, is this big function R, that depends on these 2 quantum numbers, N and L. And the other one is the spherical harmonics, depending on the angles, and depending on these 2 quantum numbers, L and M. Okay, so last class, we finished finding the radial part for the ground state. So the ground state is one for which N is 1. So N1 is the ground state. And we said that when N is 1, the only possible value for L is 0. So we found that our N1 L0. Why L can only be 0? Because remember, the solution for the radial part has many components, many pieces, and I'm writing them here. This rho, as we said, this rho is R over AN. This rho originally introduced as kappa R. We found what kappa is, and so we are saying this rho is R, is our variable, but divided by AN. Okay, there are people coming. Amit, James, and Michael. Okay. And then the issue about how to decide the values of L comes from this V part of the solution. Now, the V part of the solution is a series where we have this J going from 0 up to N, little n minus L minus 1. So this series will only make sense if this thing is at least 0 or larger than 0. So when we put N equal to, when we put N equal to 1, what survived in this top part of the series was minus L. So the only L that makes sense here would be L0. So this is the function that we found last class. What we are going to do today is, let's look at now the first excited state. The first excited state is N equal to 2, which means the energy now is E1 over N squared. So this is E1 over 4. And oops, there is more people coming. Sangeeta. So remember what E1 was? The ground state, minus 13.6. So the first excited state is minus 3.40 eV. What we want to find now is the solution, the function, the eigenfunction for this first excited state. So what is that? Well, the whole solution will be, for N, I substitute number 2. For L, we'll have to decide, and for M, we'll have to decide, okay? And, well, this depends on R, theta, and phi. So here we have the part that is the radial part, where N is 2, and L we have to decide, as I said. And the part where here we have L and M, theta, and phi. So this part here, I hope you already started doing the problems that I suggested. So this part here, you already know how to solve from what we talked about before. What I'm going to do is solve this one with you. Okay, so if I solve this one and you combine with the spherical harmonics for N2, you have the whole solution. Okay, so that's the procedure. So we are just going to do the radial part now. All right, so then comes the question. For n equals to 2, what will be the values of L? Well, coming back to what I just said, we'll have to determine the values of L using this sum. Now, where does this sum make sense? Well, so if n is 2, that sum for the v part of the solution that goes up to n minus L minus 1 means that we are talking about a sum that goes from J0 up to 2 minus 1, so it becomes 1 minus L. Okay, so you see that there are two possible values now. One value is L0 as before. This works because this would mean a sum that goes from 0 to 1, so we'll have two terms in this sum. But another possible case is if L is 1. If L is 1, that sum also makes sense. It will go from 0 to 0, so we'll have just one term as we had before. So you see that things now have changed. When we are talking about the first excited state, there are many possible states that will have that same energy. What are they? Well, we could have n equal to 2 and L0. In this case, the only possible value for m is 0, because remember, m goes from minus L, skipping integers, plus 1, plus 1, plus 1, all the way to L. So if L is 0, as it is here, m can only be 0. So this is one possible wave function that has this energy of the first excited state. So n2, L0, M0. Okay, so this is one of the orbitals. Now, we could also have L1. Now, with L1, then we have three possibilities for m. We have m minus 1, we have m0, and we have m1. So all of these other wave functions are also solutions with that same energy. So what are these other possibilities? N2, L1, and m minus 1, or N2, L1, and M0, or N2, L1, and M1. Okay, so for the radial part, all of these three cases here will have the same radial part is 2, 1. But the spherical part, the spherical harmonics part, will depend on what we choose here for m. Okay, so there will be different solutions. Here, we are just going to look at the radial part. But before going into this case, let's start with the case where L is 0. Okay, so I'm going to be looking first at this solution, and later we are going to look at this other solution. Okay, so for this one, what is the R that we have? I'm going to put here the rho. The rho is to the power L plus 1, but L here is 0, so the power will be just 1. Then we have the exponential of minus rho. We have the V that we'll have to write divided by R. Okay, so what else do we have? We said that rho is that R over AN. N in our case now is 2, so I'm going to rewrite this as wherever there is rho, I'm going to put R over 2A, so this is this piece, exponential of minus R over 2A, everything divided by R, so you see that this will cancel. And we have the V part, which is the sum. So let me write what that is. We said that is from J0 to N is 2, minus L, which is 0, minus 1. So we have a sum from 0 to 1, we already said that, of C, J, and rho J. Okay, so you see that we have two elements here. So I'm going to put our V with those two elements there. Is the C0 when J is 0, so rho to 0 is just 1. And the other one is the C1 row 1. Okay, so this is the V part. Well, let's think a little bit more. The C0, we already said last class, how do we find it? Normalizing. How about the C1? Well, the C1, we had that recursion formula. So that's how we are going to obtain that C1. So let me write the recursion formula again. So if I want to get the Cj plus 1, what I have to do is 2, now I'm copying from the book, j plus L plus 1 minus n. And then here j plus 1, and then j plus 2L plus 2. Cj. Okay, so this was the recursion formula that we talked about. Of course, you don't need to know that. No, this is something that is given to you. So if I have C0, how am I going to obtain C1? Well, wherever there is J in this equation, I'm going to put, so wherever there is J, I'm going to put 0. L in our case is 0. N in our case is 2. So if you put all this here, we get 2. Here is 0 plus 0 plus 1 minus 2. So you see that all this just give us minus 1. In the denominator, we have 0 plus 1, so it's just 1. And then we have 0 plus 0 plus 2 is just 2. Okay, so all that tells us that C1 is 2 minus 1 divided by 2 of C0. So C1 is just minus C0. Okay. So now that I have C0 also, I'm going to rewrite the V. I'm going to put it here. We already canceled the r, so we have exponential of minus r over 2a divided by 2a. And now this part here, I'm going to put C0 in front because both have C0 and C1 we just found is minus C0. So we have 1 minus rho. And what is rho? R over 2a. Sorry, this is not V. This is R. Okay, so then we've got our solution for the R when n is 2 and L is 0. That's it. So it's not the end of the world. It's simple. It's just some euphemism coming. No, so it's not the end of the world. It's just following this procedure. Now, what is the next step? If you want, normalize and find C0. Okay, so with that, I repeat, you come back to the whole wave function. You put the R20 that you just found. You attach to it the spherical harmonics that you found before. And we are done. Okay. All right. So now let's go for the other eigenfunction that still has the same energy of the first excited state, still has energy E2, which is the wave function where n is 2, L is 1 now, and m can be 0, can be minus 1, can be plus 1. Okay? So as we said, I'm just going to look at the radial part, and then you attach the L, the spherical part later. See, so let's do this one. Okay, so what is that? Again, the procedure is the same. Rho is R over 2A. Okay, so rho here is R over 2A. I'm thinking about the first term here is the rho to L plus 1. Now, L, in this case, L is 1. So you see that this will become squared. Okay, good. We have the exponential of minus rho. So rho is R over 2A. We also have R in the denominator, and we have our V. Let me get some space here. Our V function is a sum from J0 to what? N is 2, L is 1, and minus 1. Well, the sum goes up to 0 of Cj rho j. So you see that R to 1. The R square will cancel the top here. So I have just R in the top, and then 4a squared, exponential, and then, well, the sum is just the C0. So that's it. So we are done with this function. Final step would be to normalize. Okay, so then this is the procedure, and there will be many exercises for you to do, combining both the R part and the spherical harmonics. But you see, there is no mystery, it's just derivatives and algebra and sums is no big deal. Okay, but what we concluded from this game is that for each value of n, I may have many solutions with the same energy. No? So n is that principal quantum number that tells us what is the energy of the system. But for each n, we can have many L's and we can have many M's. No? What did we find last class? We said that for a given n, L can be 0, 1, 2, all the way to n minus 1. Okay, so for a given n, we have these n possible values of L. And for each L, we have many possible values of M. No? M goes from minus L plus 1, minus 1, 0, 1, all the way to L. So we have 2L plus 1 values. So you see how many degenerate states we can have for a given n. Yeah? For the case of ground state, N1, that was very simple. We had just one state. So I'm going to put here just one possible state. For the case of N2, where L could be either 0 or 1, then when L was 0, we had M0. But when L is 1, we can have M minus 1, 0, and 1. You see that now we have 4 states, all with the same energy. And then if you do N3, you see that things start becoming a nightmare, no? Because we have for L0, we have M0. For L1, we have M minus 1, 0, and 1. And for L2, we have M minus 2, minus 1, 0, 1, and 2. If you count, here we have 5, here we have 3, here we have 1, and now we have 9 states. And if you continue with this game, you're going to realize that for each n, there are n squared degenerate states. N squared degenerate states, no? N squared states all with the same energy. And you could even come up with this. Well, either you go one by one as we are doing above, or you can come up with this with a sum. How? You would say, okay, for a given L, we concluded that we have 2L plus 1 possible values of M. Okay, for a given L. But for a given N, my L can go from 0 all the way to n minus 1. So this gives me how many degenerate states we have, this sum. And this is a sum that you played with in the past. Now, this is an arithmetic series sum. No? So if L is 0, we have number 1. If L is 1, we have 3. If L is 2, we have 5. So you see, we are summing, but just odd numbers, all the way to 2n minus 1 plus 1. Okay, so what is this? Sum is 1 plus 3 plus 5, all the way to 2n minus 2 plus 1 to n minus 1. And you may have, no, I'm sure you learned before, how do we get this sum? The first term plus the last term multiplied by how many we have, and we have n terms divided by 2. And then you will see that we get that n squared. Okay. So n squared degenerate states. Okay, so we are about to finish this discussion about this R, the radial part. I just want to conclude by saying that that V part of the solution also gets a name. Remember that when we are talking about the solutions of the spherical, the spherical harmonics, no? We said that we had this PLM, which is, we said, oh, these are the associate Legendre's functions, no? And we also had the part that depended on phi and some normalization here. But this had a name, we had an equation to derive them. Okay, now the V part of the radial solution also has a name. It's also known to the mathematicians. It's, I'm going to write the symbol. It's this big L, and this big L is coming from the name associated Laguerre, is the person who studied them, function. So again, there is an equation for you to find all of them. Depends on n minus L and 1, and here 2L plus 1, and here 2 rho, and we get that, okay? What is the equation? It's in your book. Instead of writing here, I'm going to show the equation in your book, because I'm going to take the chance now to also show you some drawings for the solutions. Now let me see how I get out of this. I wanted to show to you. Here. Okay, so let me get out of this. I'll come back later. And now I'm going to share from my computer here. Okay, so you see, let me make this big. This was what I was saying. No, the V part of the radial solution has can be written in this form, where these L are those Laguerre's functions. How do I get these L's? Well, you can just follow this equation. You see again, the function is written in terms of another L, which is a polynomial. And then this, to get to that polynomial, you follow that equation. It's very similar to what you had before. Of course, the equations are different. Okay, so here they are giving us a list of these Laguerre polynomials. No? And you just substitute the x by the 2 rho. Very well, but that's not why I came to this. I came here to show you the figures. So now, as we said, let me see if I have an equation here to show. So now, here, yeah. So now we have all of the solutions for the time-independent Schrödinger's equation when the potential is central. So this is the solutions. And as we said, n determines the energy. This little n here determines the energy. And for each n, there are many L's, and then there are many M's. What do these L's and M's give us? So these are the figures that I wanted to show to you. You see, this first column here is the case when n is 2. Okay, so all of these are drawings of the wave function, the absolute square of the wave function. All of them have the same energy, but you see that the drawing changed. And what does this drawing give us? This is giving us the probability for finding this electron in this first excited state. So it's, remember we were talking about Bohr last class. No? So Bohr was wrong. He was talking about a specific trajectory around the proton, around the nucleus. Well, that doesn't exist. What we have is a cloud, no? Distributed around that proton. And what is the shape of this cloud is giving us the largest probability. What is the largest probability for us to find that electron? Okay, so that's why I just wanted to show you this figure. So all of these different drawings here, all of these absolute value squares, the wave function on this column, give us the same energy. This is N3, and you see how many more possibilities we have. Okay, I'm going to stop sharing this now. I'm going to come back to the tablet because we are going to conclude this topic. There are problems now that you can solve that I'm going to put in the announcements as well. Whenever there are these single star, these are problems that are very important. These are the ones that I've been selecting throughout the course. Okay? and I'm going to put them in the announcements. Okay, so now I'm going to come to this part, which is what we talked about before, last class, about those lines that they were looking at for the hydrogen atom, and then we are going to conclude this part. So let me stop sharing and come back to my tablet. Okay. All right, so the end of this, oops, let me make this a little bigger. The end of this discussion now is coming back to where we started last class. What we said, well, from experiments much before the birth of quantum mechanics, people were saying, like, I have a recipient with some kind of gas, for example, gas of hydrogen. I excite that with some discharge, I excited those atoms, and then those atoms don't remain excited forever. They eventually decay, and when they decay, they emit some radiation. And people are finding those lines. Each kind of atom was given a different sequence of lines, like these were the fingerprints of the atoms, And well, they had no idea what this was, and they were trying to make sense of these lines, coming with equations for them. So each line is associated with a different wavelength. So wavelength means different frequencies. Different frequencies means different energies. So these lines, this is the spectrum of the atom. Okay, and then I gave to you an equation that Rydberg came up. There were many people studying these lines. Each person would come with a different equation, and Rydberg combined them. But where were that equation that I gave to you coming from? Now we know, when we started with Bohr, we started understanding, and now we understand it much better. So we have here the nucleus, and we have many possible orbits for this electron, even though it's not only an orbit in the sense that Bohr had in mind of like a planetary system, as we just saw. It's a cloud. This electron is not a single particle, it's a wave. But depending on the energy of this electron, maybe the probability for finding it will be larger far away from the proton, if the energy is high. Anyway, but if the electron is in some energy, some excited energy, when it decays to a lower energy, then it emits a photon, which has some energy. And what is this energy? Is the difference between the energy that it had in this initial state to this other one. So the energy that it emits is the initial minus the final. And what is this energy? Is, well, minus 13.6, as we found before, 1 over Ni squared minus 1 over Nf squared. So Ni means the initial state, and Nf is the final state. Okay, so that's the energy that comes out. Important thing here, as the electron moves from this I state to the F state, what we call is this transition, and we say that this is a quantum jump, which is a strange thing of quantum mechanics again. Is the electron kind of disappears from here and appears there. It doesn't pass through these intermediate states. Now, there are no intermediate states. It disappears from one level and appears in the other. That's what people call a quantum jump, which is a strange thing, one of those strange properties of quantum mechanics. Okay? And when it disappears from this level and appears in this other level, it emits this photon with this energy. Okay, now, as we just said, energy is associated with the frequency. we are talking about electromagnetic waves, no? So moving with the speed of light, no? And see, here's the speed of light. So I can also write a frequency in terms of wavelength. No? So we can rewrite this equation here as I gave to you last class, in terms of the wavelength of those lines of the spectrum for the hydrogen. So what is it? A certain constant, and here 1 over nf squared minus 1 over ni squared. Okay. What is this R? Is the constant that I gave to you in last class, is the Rydberg constant. So 1.097, blah, blah, 10 to 7, 1 over meter. When I wrote to you last class, I wrote to you like this, 1 over 2 squared and n squared. What is this 2? Is the final state. So we have here N1 is the ground state, N2 is the first excited state, N3, N4, N5. So if we decay to N2, this is the energy, and this is the wavelength that we will find. When the hydrogen atom, when the electron decays into this first excited state, the lines that we get are the visible, in the range of frequencies that we can see. So this was the first one that people started studying. And this, well, the first person studying that was Balmer. But if it decays, there are many other lines. If it decays on the first excited state, oh, sorry, this was the first excited, but if it decays now in the ground state, then these are in the ultraviolet and also gets a name. If it decays into the second excited state, this becomes infrared and also has a name. Okay. Anyway, so this is the end of the story, connecting with the previous class. Now, what I'm going to move to is discuss, we are coming back now to discuss the spherical harmonics. There was a complicated equation. We didn't solve that equation. Now we just gave you the solution. But now let's try to understand where that solution came from. Those solutions for the spherical harmonics, they're associated with what for the hydrogen atom? The radial part depends on N. N is dependent on the energy. Very good. How about this part now? We got those different shapes, those different clouds, but where are they coming from? What we are going to discuss now is angular momentum. What we are going to see is that these guys, they are the solution, and they are the eigenfunctions for the angular momentum. Okay. So that's the new section 4.3 in the book, which is very important. It has some, it reminds us of what we've done for the harmonic oscillator. Okay. Let me just see if there is any question. Nobody's seeing anything. Let me just see. No, nothing in the chat. So then I continue. Okay, so let's talk about angular momentum. Thinking about what you learned before in classical mechanics. What is the definition of angular momentum? We usually use this L. So many L's now. No? This has nothing to do with the Laguerre function that we saw before. This is L angular momentum. And what is the definition? The R cross product with P momentum. So how do we find the X, Y, and Z components of this angular momentum? Well, let's put it. Here we have X, Y, and Z, and the P we have Px, py and pz. Now we are thinking about 3 dimensions. And if we want to find Lx, I go like this. So Lx is y pz minus, if you want to put that other column to help, minus zpy. The ly is going to be, let me put a different column, the zpx. And if you want, you can put this extra column here just to assist finding us this negative part, minus x pz. And again, and you can do the same for the lz. The lz will be x py minus y px. Okay, this you already knew. This is classical. What is going to change now, if we go into quantum, in the quantum domain, is that, well, now the things will be operators, right? So if you want, we can even put the hats here, and these guys will be all operators, as we've been doing so far. And momentum operator, you know very well what it is, but now we have momentum in the x, in the y, in the z direction. So here we'll have derivative in x, but then for the y is the derivative in y, and the one in z, derivative in z. So that's what is new. We would just have three direct directions, x, y, and z. Okay, now we know that position and momentum do not commute, but they do not commute if we are thinking about the same direction. Okay, if I put y with px, well, they commute, they are in different directions, but in the same direction, they do not commute. Okay, well, what is the consequence of this if we are now thinking about the angular momentum, the components? You will see the same thing, that Lx, okay, so same thing, not true. Just as position and momentum do not commute, the 3 directions of the angular momentum do not commute. Okay, so maybe I was not very clear now. Let me try to explain. Position and momentum do not commute if they are in the same direction. If they are in different directions, yes, they commute, they are not aware of each other. But angular momentum in the different directions, x, y, z, they do not commute. Why? Because you see that the x here has components in y and z, and the y here has, again, components in z and x. Now, so you see that there is z components here, and there are z components here. Okay, so when we are thinking about position and momentum, they will not commute if they are in the same direction. But if we are talking about angular momentum, none of them will commute. Okay, so x and y does not commute, x and z do not commute, y and z do not commute, and let's check that. Okay, so none of the directions of the angular momentum will commute. So we say that these 3 directions, L, Y, and Z, they are non-compatible. They're incompatible. They don't commute. Okay? Remember this word that we talked about before, these incompatible observables. So let me put them. Okay, so then let's just verify what we just said. We said that they do not commute. Let's double check. So I'm going to put Lx and Ly, and let's check what we get here. You see that I'm not putting the hats because it takes too long, cumbersome to write, but if you want, you can put the hats. We are talking about operators, no? Okay, so let me just copy what Lx is. Lx is up here. So I'm going to copy this Lx here. It has the y and the pz, all operators, minus z and the py. Okay. How about the ly? The ly is the z px minus x pz. I just copied what we had above here. And then I said, well, the lx and the li, they do not commute. Why? Because here we have pz and here we have x, and these things do not commute. So here I have z and I here have pz, so they do not commute. Okay, but let's open this commutator. So there were some problems that you did in chapter 3 about commutators. When we have sums or differences as we have here, we can open this commutator. So let me start by doing this. So I'm picking this first element here, y pz, with this guy, so z px. Again, this guy, y pz, with the last one. So you see that I have a minus sign here because of this minus sign. So y pz with x pz. Then I'm going now to switch to this term. So I have minus z py with z px. And the last one, this is minus, it becomes plus z py with the last one, x pz. Okay. All right. What do we get from here? Also from chapter 3, there was a property of the commutator that you verified, that if you have A, B, C like that, you can write as A of BC plus A of BC plus ACB. Remember this. So I'm going to use this property to play with these commutators. Okay? Now, there are 4 elements, not 2 and 2 here. But the only ones that we really care about are the ones that do not commute, which is the PZ and the Z. The others, they commute. So I can just take them out of this commutator. So I'm just going to write that whole complicated thing. Instead, I'll put Y. Then I have the PZZ and the PX. Okay? Because it's true that we could look at the commutator y, z, px with the pz, if we were following this rule that I mentioned before. But y does not commute with z. Y does commute with z. Y just does commute with pz. So all this is 0. So I'm not bothering writing this term. Okay, I'm just keeping here the term that I know does not commute. If this is not clear, let me know, scream there, okay? Okay, so from this term, I just kept this guy, and the other ones, I put them out. How about this other guy? Okay, so you may say, oh, I see 2 terms here with the same direction, the PZ and PZ. Well, but they are the same thing. So this commutator PZ with PZ is 0, and all the others are different directions. So I don't need to put that term. That term is just 0. Let me go for the other term, this 3rd term here. Again, the only things that are in the same direction is the z, but it's equal to the other term z. So again, this one is 0. I don't need to worry about that. So let me go to the last term. And the last term, what will survive here? You see that we have the x, we have the py, and here I have z and pz. This one I have to care about. This one does not commute. Okay. Okay. And what is the commutator between x and p? We wrote it here. No? So the commutator between z and pz is IH bar. So I'm going to write this as y. The commutator here, this is just inverted position of P and Z, no? So minus IH bar Px plus X IH bar Py. Okay, so that means we have IH bar of, I'm going to write this term first, X Py minus this term minus Y Px. Okay, so the commutator between Lx and Ly is this. And what is this? We've seen this term before. If you go up to what we wrote, you will see that this is the Lz. So this is the Lz. Conclusion, Lx and Ly do not commute. And the commutator between them is equal to IH bar, the third direction, Lz. And you can repeat what we've done here for all the others, and you will find a pattern, which goes like this, cyclically. From X, as I go Lx, Ly, so from X to Y, I get the Z. Okay, now if I go from Y to Z, so if I look at the commutator Ly, Lz, what I get is the X, IH bar Lx. If I now do the commutator from Lz to X, Lz to Lx, I get IH bar Ly. Okay? So if you follow this cyclically, you're going to get all the three commutators. You can double check that. If you invert any of them, if, for example, if I ask, what is the commutator between Lx and Lz? Well, we just have to put a minus sign here. Okay. All right, so all that to say, or to conclude, they do not commute. They are incompatible. Incompatible observables. And this has a very important consequence. We talked about this at the end of chapter 3. Whenever we have two operators that do not commute, what does that mean? That I cannot measure both with absolute precision. That both have to satisfy the uncertainty principle. Remember that we said that? So we said that if A and B do not commute, that means that I cannot measure A and B exactly, and there will be an uncertainty. The product between the two will have an uncertainty that is larger than the commutator between A and B, the expectation value divided by 2i, all this squared. So we did this, we already knew that for position and momentum. We put the commutator that this is h bar over 4. So this is larger than h bar over 2. And now you see that for angular momentum, same thing happens. So we cannot know the angular momentum in the x and in the y direction of the electron with absolute precision, or the x and the z, or any pair cannot be measured with absolute precision. There will always be an uncertainty. Okay, so what is the uncertainty if I'm thinking about Lx and Ly? So I'm going to follow the equation that we talked about. Remember, I gave you this equation. I said that you should look at the book to look at how it is derived. No, it's no big deal. You can understand. Okay, but just following this equation, the uncertainty for x and y will be, well, let's just copy that. Commutator between x and y we saw is IHLZ. Okay, so this is the commutator, expectation value divided by 2i, all that square. So you see that the i's here cancel, and so we have the h bar square 4. So this part looks similar to the x and p, but in this case, we also have the LZ square. Okay. So we cannot, and the same relationship will happen for x with z, y with z, now any two pairs. Okay, so if they do not commute, if they are incompatible observers, we cannot measure them at the same time with absolute precision, and they do not have the same eigenfunctions. Okay, so if operators do not commute, they have different eigenfunctions. So the eigenfunction of the operator Lx, I don't know, is different from the eigenfunction of Ly. Okay, so x and y are not the same. But if I have two operators that do commute, let's say operator A and B, if they do commute, that means that the solution of the eigenfunction of A and the eigenfunction of B, they are the same. Okay? So this is when they are compatible, which is not our case. In our case, the eigenfunction of x, of y, of z, they are not the same. Okay, so what I want to find out is there any combination, or is there any pair that I could find that does commute for this discussion about angular momentum? Is there any pair that would commute? And the thing is, if I look at L square, so L square means the small, let me put the square of the total angular momentum. L square is Lx square plus Ly square plus Lz square. And the interesting thing is L square does commute. So L square does commute with Lx. L square does commute with Ly. And it does commute with Lz. Okay? And you can check. Let's check one of them. Okay, so let me pick, I don't know, the book does with Lx. So let's pick the last one. Let's pick with Lz. L square with Lz. Okay, so what is L square? Lx square plus Ly square plus Lz square of Lz. Okay, we said that we can split the sum into sum of commutators. So we have Lx square with Lz. We have Ly square with Lz. And we have Lz square with Lz. Well, Lz square and Lz is the same thing. They commute. No, it's 0. But these guys, we know they do not commute. These are the different directions. No? So remember the property that I mentioned to you here. Let's see where it was so long ago. Here, yeah. So this is a relationship that you worked in one of the problems from chapter 3. And I'm going to use this now for this part. Okay. So what do we have when I'm writing Lx square Lz? This is equivalent to saying Lx, Lx, Lz. So I'm going to use that property of commutators, and I'll write this first term as Lx out of Lx, Lz, plus, now I'm putting this one out to the other side, Lx, Lz, Lx. Okay, so this is this first term. How about the y term? The one that involves y. This is going to be Ly, Ly, Lz, plus Ly, Lz with Ly. Okay, so this is opening this commutator. All right, so now what do we have? Lx, Lz. We know that it's going to give us Ly. We just need to decide if it's plus, if it's minus. So let's go to our cyclic game. No? So what we are doing here is we are not going clockwise. In this case, I'm going from X to Z. So I'm going counterclockwise, which means I have to put a minus sign. Okay, so here I have Lx minus IH bar Ly. Okay. Okay, now this guy, again, is the same thing, no? Lx, Ly. So it's going to be minus IH bar Ly with Lx. Now, this term, we are going from Y to Z. So this is good. I'm going clockwise, no? From Y to Z. This is plus, going to give us plus IH bar Lx. So we have Ly plus H bar Lx, and the next one is the same thing. No? So plus H bar Lx of Ly. And you see that here I have X and Y. Here I have X and Y, but with a different sign. So these guys cancel. Now the other one is Y and X. This also is Y and X, but different signs, so they cancel. Okay, so as we said, L square does commute with Lx, with Ly, and with Lz. Very good. So if it does commute, that means that there is a solution, there is an eigenfunction, or many eigenfunctions for Lz. I'll call these eigenfunctions f, with some eigenvalues me. And these eigenfunctions will also be eigenfunction of L square. I don't know yet what the eigenvalues is. I'm going to call it lambda. Okay, but this is the same because L square and Lz, they are compatible. Now these are operators that commute. So what we are going to do now is we are going to try to find the eigenvalues, me and lambda. And then at the end, what you will see is that if you write this L square in terms of spherical coordinates, we are going to recover that all the equation that we had, the equation for the y, there was L plus 1, and y. Remember that? No, the complicated equation. Well, this is exactly this one. Okay, but now we are going to be writing things in the, well, instead of solving that equation, trying to find the eigenvalues, we are going to do it in a much simpler way, playing with the angular momentum. Okay, all right. So I'm going to rewrite L square and total square of the total angular momentum has these eigenvalues lambda. We don't know yet what it is. We are going to try to find. And Lz has the same eigenfunctions with different eigenvalues, and we are going to try to find them. Okay. Well, in this process now, we are going to get inspiration from the harmonic oscillator. We are going to introduce, remember that in the harmonic oscillator, we introduced that A plus and A minus, the raising and lowering operators. Well, we are going to do the same game here. I'm going to introduce some L plus that we are going to define as Lx plus ILy. And L minus will be Lx minus ILy. And you will see that this will be very helpful. First thing that we need to do, you will see that at the end, this will be raising and this will be a lowering kind of operator, okay? So these are what we call ladder operators. Okay, but how we are going to find that? first thing that we are going to do is play again with the commutator. So let's look at LZ, the commutator between LZ and L plus first. Well, it's LZ, oops, LZ with LX plus I LZ with LY. So you can, so if we know what these commutators are, so you put all these together, you're going to see that we get plus H bar and then L plus. If you do the same thing now, if we do the same thing now with L minus, what changes in this story is just this minus sign, and here we'll have a minus, okay? If you do, so this is the commutator with LZ. If you do with L square, what do you think is going to happen? With L square, well, L plus is X and Y. L square commutes with X and Y, so this has to be 0. And the same thing, if you put the minus here, it has to be 0. How is this going to help us? Remember in the story of the harmonic oscillator, we said the following. If I have one solution, I know that A dagger of A plus is going to be a solution, A plus of A plus is going to be a solution, and so on. We said that. Now it's the same story here. If I have one solution, F, the L plus is also going to be a solution, and the L plus of the L plus we're also going to do a solution, and so on. And the same thing the other direction. The L minus will be a solution, and the L minus of the L minus will be a solution, and so on. So that's how it's going, this is what is going to help us to find the eigenvalues. But let's first prove that this is true. Okay, so let me erase this. So what we want to show now is if F is an eigenfunction. Is an eigenfunction of both. No? If it's eigenfunction of L square, it's also an eigenfunction of LZ. So if F is an eigenfunction, then L plus F will also be an eigenfunction. Well, let me check. So I'm going to put L square of this and see if I recover this function. Yeah. We just saw above the L square with L plus is 0, which means I can write L square L plus minus L plus L square is equal to 0, which means L square L plus is equal to L plus L square. So I'm going to rewrite this as L plus of L square and the function. Well, but I said that F is an eigenfunction of L square. So this means L plus lambda F. But lambda is just a number. I can move it. And I have lambda L plus function. So you see, this new function here is an eigenfunction of L square. Good. Okay. Now what we want to show is, how about the LZ? Is this L plus F? Is this also an eigenfunction of LZ? It should be. And well, let's check. So to do this part now, I'm going to use the commutator between LZ and L plus. And we said this is not 0, no, they do not commute. We found that this was plus H bar L plus. Okay, so then that means I can write LZ L plus minus L plus LZ equals to plus H bar L plus. So that means I can write LZ L plus. LZ L plus is what I see here, you see. So I can rewrite that as L plus LZ plus H bar L plus. Okay, so that's what I'm going to put up here. So instead of this, I'm going to use the right side. So I have L plus LZ of that function plus h bar L plus of this function. Well, we said that f is an eigenfunction of LZ. So this guy is me f. It's the eigenvalue. I don't know yet what this eigenvalue is, but it's me f. So I can rewrite this as, this is a number, I can move it around. So I have me L plus f, and I have h bar L plus f. So these are numbers. I can rewrite this as me plus h bar L plus f. So this function, this whole function is an eigenfunction of LZ. What changes is the eigenvalue. Now the eigenvalue increased, just as we used to do with the A plus in the harmonic oscillator. Now we increase. And if you do the same game now, let me see if I get a different color here. So if I do now this with the L minus f, it's also going to be an eigen, this whole thing will also be an eigenfunction of LZ. What is going to change, go through this whole thing, is this minus here. So wherever there is plus before, we're just going to have to put the minus. So this will be the minus. Okay. And then we get, and here we have a minus. Yeah. Okay, so, and then you can double check that. So conclusion of this story, let me just summarize. If I have an eigenfunction from L square, then L plus f will also be an eigenvalue, will also be an eigenfunction with the same eigenvalue. And L minus will also be, L minus f will also be an eigenfunction with the same eigenvalue. So for the L square, either this function or any raising function, lowering function, they all have the same eigenvalue lambda. Okay? Now, so they're all degenerate here. Now, for the LZ, if I have this function f, the L plus f will also be an eigenfunction, but careful, this becomes plus. So the L plus is the raising operator. And the L minus of this function, this new function here, will still be an eigenfunction of LZ, but with a different eigenvalue. Okay, so the eigenvalues now on the Z side, they do change. Okay, all right, so very similar to what we did in the story of the harmonic oscillator. What we are seeing is that the L plus is raising the eigenvalue for the LZ. The L minus is lowering the eigenvalue, but this cannot go on forever. It should be a point where this has to stop. Where does it have to stop? Well, if I am, so the eigenvalue of LZ increased. So let me write this here. Suppose I start with a certain eigenvalue for the LZ. I apply the L plus, this is raising. This is, and then I apply it again, this is raising. But there will be a point that this eigenvalue is the value of the angular momentum in the z direction. There will be a point that it will get larger than the eigenvalue for the total angular momentum. So the eigenvalue for LZ, one portion of the angular momentum, cannot be larger than the total, the eigenvalue for the total angular momentum. Yeah, because this is just a portion, it's a piece. Remember, L squared is Lx squared plus Ly squared plus Lz squared. So I go on increasing, but there is a point where this thing has to stop. Okay? So there should be a top wave function so that if I apply the raising operator on it, it stops. It cannot go beyond. Okay? So there should be this stop, and the same thing about going down and down. There should be a bottom wave function so that if I apply the lowering operator, this will have to stop. Okay, so this will help us find, with this game, just as we did before for the harmonic oscillator, this will help us finally find what are those eigenvalues for the LZ and what are those eigenvalues for the L square. Okay, but I see that it's already 10:43. So I think this is enough. I can stop, and I want to talk to you just a little bit. Oh, come on. So let me stop recording. Where is it?